Okay, hello everyone. Welcome to the online portion of the astronomy presentation for the 2022 Science Olympiad Summer Institute. So our Astronomy 2023 event will focus on the topic of stellar evolution and stellar variability. And the 2023 National Tournament, which is very exciting, will be back on site at Wichita State University on May 19th and 20th of 2023. So get excited. We'll be back in person for Science Olympiad in 2022 and 2023. And so this will just be a quick overview of the astronomy event. And of course, there'll be a lot more detail in the actual in-person SOSI session this summer. And so just a disclaimer before we get going, this entire presentation was created using the draft rules for the event. And so there may be some changes in the final copy of the rules. This final copy of the rules will be released in the fall on Tuesday, September 6th at soinc.org. It'll be publicly available, and those will be the official rules for the 2022-2023 season. So there might be some small, minor changes between what I'm discussing here today and what will appear in the actual rules for this year, but the changes should not be too major. Okay, with that in mind, here are the draft rules for the event this year. So this event, before I get to that, is sponsored by the NASA Universe of Learning STEM program, and I'll be telling you much more about that at the end of this presentation. So here are the draft rules. The basic description of the event and the parameters have not changed drastically from previous years. The main change here, the changes are in bold, is to focus on stellar evolution and variability, but the event parameters are exactly the same as previous years. So teams can bring information in the form of a binder and or a computer and or two of those. And so the teams have a broad range of leverage in choosing exactly how they want to prepare their information, their resources, and their research for use in the event itself. And one thing to note is, as in previous years, students may be asked to access a dedicated NASA image analysis website to answer questions using the software JS9, which is a version of the DS9 software that is publicly available on the internet for students to use. And this is a version of the astronomical software that astronomers use to do image analysis. So this is kind of our astronomy equivalent of hands-on activities. And so that's why the JS9 part of the event is so strongly focused on each year, especially at nationals, is because we want students to have the chance to actually do hands-on astronomy. And this is really the only way to do so, because astronomy, right, it's done at night, it's not done in the classroom. But what astronomers do during the day in their offices or in classrooms is analyze the images that they took at night. And so the students can analyze those images themselves using JS9 during the competition to get a flavor for what astronomy is actually like. So that's just a brief rundown of the description and event parameters. They're very similar to previous years, except now we're focusing on stellar evolution and variability, broadly speaking. And so the competition for this year, everything again in bold, is what's changed from previous years. You can see it's generally pretty similar to previous years. Every year in astronomy, we focus on stellar evolution and understanding stellar evolution using these basic diagrams and relationships that are fundamental to astronomy. So we expect students to be able to show how stars evolve on the Hertzsprung-Russell diagram and study stellar spectra and light curves to infer properties of stars, and use simple equations like cosmological distance equations to infer properties of stars. And so this first part of the competition has not changed from last year, and it almost never changes very much, because we really want to focus on the same fundamental principles that astronomers use to understand our universe. What has changed a little bit in the event this year is the specific types of stars that we're covering. And you can see those are in bold. So this year we're adding pulsars, we're adding semi-regular variables, symbiotic variables, globular clusters, population 1 and 2 stars, Wolf-Rayet stars, classical and type 2 Cepheid variables, luminous blue variables, X-ray binaries, and different types of supernovae, along with type 1a supernovae, along with kilonovas and gravitational waves. So we're really expanding the reach of our event quite a bit this year to include a broad range of types of stars and astronomical events. And then section B of the competition shows the specific physics, the astrophysics principles that we include in our event. Again, you can see most of this hasn't changed from previous years. We always include things like orbital mechanics and Kepler's laws and calculations of distances to objects, for example, by using parallax. What we're using here that's new is using the period luminosity relationship to calculate distances and changing the wording of the rules to focus on using the radiation laws to answer questions related to stellar evolution and structure specifically. And so the last new part of the rules is our deep sky objects. These change every year. We always rotate them out in order to make the event fresh year to year. And so we always have on the order of 15 deep sky objects. Here they're sorted by type, and I'll give you a brief kind of taste of them later in this, but you can view our slides to really view them in detail, and we have links to each of the detailed information on the deep sky objects from NASA websites that are contained in the presenter notes of this slide deck. So if you want more information on these deep sky objects, please just view the presenter notes of this slide deck. Just to briefly classify them, so we have two miscellaneous deep sky objects. One's a globular cluster, 47 Tuc, and one's a planetary nebula, NGC 7027. We have different types of stars, including a classical type 1 Cepheid, W Virginis, which is a type 2 Cepheid. We have Wolf-Rayet stars, we have a Mira star, and we have a luminous blue variable star. We have some binary systems, including SS Cygni, which is the canonical dwarf nova. We have a symbiotic binary system, and we have an X-ray binary X9, which is contained within the globular cluster 47 Tuc. And then additionally, we have some supernovas and stellar remnants, including a gravitational wave event, GW 170817, a pulsar, a type 2 supernova remnant, and a type 1b supernova remnant. And so just to kind of give you a sense of kind of the overarching astronomy and astrophysics that's contained within this event. So really, the entire event is more or less contained in this one slide. So this is a one-slide summary of stellar evolution, of how stars transition from their initial protostar phase through what we call the main sequence, where they are for most of their evolution, to their final stage where they end up being a stellar core or remnant. So this is the sequence of stellar evolution from formation to destruction. And so every single star and every single object in the event this year is contained within this sequence of stellar evolution. And so what we ask students to do is really understand the processes by which students evolve throughout these stages and why different objects have different evolutionary stages, where the primary difference between these different objects is just their initial mass. More massive objects, they live shorter lives, and they often can explode in supernova events to lead to a compact stellar remnant, whereas less massive stars like our sun, they live much, much longer lives, and they live more quiescent lives, where at the end of their lives, they do not undergo an astrophysical explosion. Instead, they simply cool and contract over time during their white dwarf phase. And so this slide is a slide that we put in every SOSI presentation in order to get across the point that stellar evolution is really a process, and it's a fundamental way to understand the evolution of astrophysical objects and stars. And we study this process in this event in a few different ways. So we have kind of our general illustration that I showed you in the last slide, but then we study this using specific examples, specific deep sky objects every year. We also study this using diagrams like HR diagram shown in the bottom left here. And this is a way to view stellar evolution in graphical form. And so HR diagrams are a critical part of the event that we include every year. And then we also study this using light curves, because stars in different parts of the HR diagram, they cause different manifestations of variability from their stage that they are on the HR diagram. And so we use these light curves in order to infer properties of stars and in order to classify stars into different stellar types. And this is especially important this year because we're focusing on stellar evolution and variability, where the variability is clearly manifested through their light curve evolution. And so this is just to show that, right, stellar evolution is a process, and we can understand it using a variety of different methodologies in this event. And so this graphic is just to kind of break down the variable stars that we're covering in this event. So everything that's bracketed in blue has a box around it. That's a variable star that's included in this year's event. And you can see there are two main types of variable stars, two groups. These are the intrinsic and extrinsic variable stars. This year, we're only studying intrinsic variable stars. We're studying both classes of them, both the pulsating and the eruptive stars. And we're studying a variety of types of variable stars, including Cepheids, RR Lyrae, Miras, semi-regular variables, supernovae, novae, dwarf novae, and symbiotic stars. So we're including a wide variety of variable star types in the event this year in order to really dig deep into stellar evolution and variability. And so this diagram, this is the HR diagram again, but now overplotted in red, are different regions on the diagram where stars experience different types of variability. So you can see the Mira instability is in the lower right, the RR Lyrae instability in the middle, the Cepheid instability to the top left of that, and the Asterotis instability strip to the top left of that. And so the idea is, right, stars experience different types of variability at different regions on the HR diagram. And so we can use the HR diagram to understand which stars are likely to be experiencing different types of variability. And so importantly, we can then understand these stars in greater detail individually by studying their light curves, because we can link the exact way that the star varies in time. So these are plots, each of them, of the star's brightness as a function of time. And you can see they each have characteristic patterns. And so the characteristic patterns are linked to types of variability, which are then linked to positions on the HR diagram. And so we can understand stellar evolution through a combination of plotting stars on the HR diagram, looking at their variability through light curves, and then inferring their properties, inferring their variability class, their variability type, and more specific properties of the star, like their luminosity and their temperature, which are shown directly on this HR diagram and are linked to other properties of the star and their evolution through astrophysical equations. And so that's just a brief overview of kind of the qualitative aspects of the event that we are covering this year. And I just want to kind of give you a couple examples of specific objects that we're covering. And so again, there's a lot more details if you look at the presenter notes, and we'll go into a lot more detail, of course, during SOSI as well. But here are just some images to really get you a sense of what we're thinking about this year. So this is NGC 7027. This is a planetary nebula that's informally called the Jewel Bug Nebula. And planetary nebula are the end states of sun-like star evolution. So sun-like stars, when they're late in their evolution, they end up expanding their outer layers into space and leaving behind a white dwarf remnant that cools off over time. And if you look at the very center of this image, you'll actually see this very bright white dot. And that bright white dot at the center of NGC 7027 is the remaining white dwarf star that's left over at the end stage of this star's evolution. Here's another example of deep sky object from this year. This is 47 Tuc, or NGC 104, which is a globular cluster. This is a dense cluster of many, many stars, what we call population 2 stars, that lie in the outer reaches of the galaxy, in the galactic halo. And so the really interesting aspect of 47 Tuc is that it contains several RR Lyrae stars, which is a specific class of variable stars that, generally speaking, are older population 2 stars. And so here's actually an example. This is a light curve of the star RR Lyrae and an image of 47 Tuc zooming in to see many of these red RR Lyrae stars. And if you view the PowerPoint of this, you'll actually see this is a movie that you can see the variability directly within the globular cluster 47 Tuc. And so globular clusters are amazing sites to study stellar evolution and variability because they have so many evolved stars that are in these regions of the HR diagram, these instability strips, in which stars are more variable. And I just want to give you a couple more examples of deep sky objects from this year, just to kind of give you a taste of what's in the event. This is an image of RS Puppis, which is an amazing pulsating classical Cepheid variable star. You can see its light curve in the lower right. This star is immense. It's 10 times more massive than the sun, and it's 15,000 times more luminous than the sun. And RR Puppis and other pulsating variable Cepheid stars are periodic and follow a standard periodic period luminosity relationship. So there's a direct relationship between the light curve period of the star and its luminosity, where stars that have longer periods have brighter intrinsic luminosity. So you can use stars like this to measure distances to other nearby galaxies. And so the distance to this one specific star, RS Puppis, was measured with a very small error due to the light echoes. You can see this kind of nebulosity surrounding the star. It's expanding over time, and by studying its expansion, you can actually estimate the distance to this object and use it to calibrate the period luminosity relationship and better understand the distances to faraway galaxies. And here's another example of a Cepheid. This is W Virginis, which is the prototype for type 2 or population 2 Cepheids. And type 2 Cepheids are Cepheid variables that are also population 2 stars. They lie in the galactic halo rather than in the disk. And Cepheids, generally speaking, are horizontal branch stars that are located within the Cepheid instability strip on the HR diagram. And they can be used as very strong estimates of distance, just like type 1 Cepheids. So both type 1 and type 2 Cepheids have their own individual period luminosity relationship. And this is shown in the diagram on the top left. So this is showing you the period luminosity relationship of the type 1 and the type 2 Cepheids. And you can see this direct correlation between period and luminosity, where the Cepheids that have longer light curve periods have higher luminosities. And so you can directly use the light curve to infer the intrinsic luminosity of the star. And then if you observe the actual apparent luminosity, the apparent brightness of the star, you can figure out its distance using, for example, the distance modulus that is shown there. And you can also see that RR Lyrae have a very shallow period luminosity relationship. And so for the purposes of this event, we generally approximate the intrinsic luminosity of RR Lyrae stars to be constant. And so from that, we can calculate the distance to faraway objects. And then we also, for the purposes of this event, can use type 1a supernovae as an even further away standard candle, we call it, or object with a standard intrinsic luminosity to calculate the distances to faraway galaxy clusters. And so this is the way that astronomers calculate distances to faraway galaxies and faraway galaxy clusters. And we'll use it in this event directly with specific examples of deep sky objects like W Virginis and like RS Puppis. Okay, so I'm going to kind of skip through the remaining deep sky objects in the event. There are many, many deep sky objects in the event this year, as they are every year. And I recommend that you, of course, come to the SOSI in-person session to learn more about each of them, and also look at the presenter notes on the slides to learn about them in more detail. You can see there's lots of amazing objects, amazing images, and we're really excited about the deep sky objects this year. And so I just want to kind of now talk a little bit about the detailed astrophysics that's included in the event. So the fundamental way that we understand the sky is through looking at light, right? We're looking at light that's emitted from these astrophysical objects and from these stars. And so specifically, astronomers use the process of spectroscopy to study the light from stars and galaxies. And so this is because all of these objects emit and absorb electromagnetic radiation, and we can study the dependence of the amount of light, the intensity that's emitted at different wavelengths, different parts of the electromagnetic spectrum, all the way from the radio to the gamma rays and everything in between, including the visible light that we can actually see. And we can use how this light is absorbed and emitted by these objects to study their properties. So for example, if we look at a continuous light source, we see a continuous spectrum. But if there's a gas cloud between us and the light source, that gas cloud absorbs some of the light, depending on what's in the gas cloud, what molecules and atoms are in the gas cloud. And then we see a different spectrum with an absorption line due to the gas cloud. But also, if we look at a gas cloud directly, we can see an emission line from the light from the gas cloud that's being emitted from the specific transition from whatever molecular species or atomic species is in the gas cloud. And so this is how we understand the properties of our universe, of stars, of gas clouds, of galaxies. We use spectroscopy. And this is a fundamental aspect of the event because we can understand stellar spectra using fundamental radiation laws. And so the first fundamental law is the Planck's law, which tells us the shape of the so-called black body radiation curves that are emitted by objects like stars. And there are a couple important laws that can be derived from Planck's law that we will use in the event. The first one is Wien's law, which tells you the relationship between the effective temperature of the emitted object and the wavelength at which it emits the most of its radiation. And then the Stefan-Boltzmann law, which tells you the relationship between the effective temperature of the object, its size or emitting area, and how much total power, how much energy per unit time this object radiates to space. And so we can use these laws to fundamentally understand the properties of stars and other objects just by studying their radiation. And so stellar radiation laws are a fundamental part of the event that we include every year. And then along with these stellar radiation laws, we also include some basic equations and relationships, and these are ways to calculate other fundamental physical properties of stars and other astrophysical objects. The first key one is the distance modulus. This is the way to relate the intrinsic brightness of an object, which is the big M, and the apparent brightness, which is the little m in this equation, and the distance of the object, which is r. And the tricky thing about the distance modulus is this includes a logarithm. And the reason why is because the astronomical magnitude system is a logarithmic system, where basically instead of being log base 10, it's effectively log base 2.5. And so this is effectively translating the astronomer's magnitude system into a easier to use logarithm base 10 system. And so you can see we also include a variety of other equations and relationships. These are largely circular motion from, for example, high school physics courses, and also Kepler's third law, which is the relationship between the distance between two objects in space and their orbital period and their combined masses. And so everything else that's in the event is basically trigonometry, so the small angle formula, and also astronomical unit conversions, for example, knowing the conversion between the astronomical distance unit, the parsec, and the other astronomical distance unit, the astronomical unit, and the other astronomical distance unit, the light year, and their relationship combined to SI units like the meter. And then also knowing the way that astronomers like to represent angles as, instead of degrees, as arc minutes and arc seconds, because we're normally thinking of very small angular separations or sizes on the sky. And then of course there's also some geometry that's included as well, because we're thinking about objects like spheres, for example. So the surface area and volume of the sphere will come up. And also the inverse square law is very useful to calculate the distances to objects, because the amount of radiation that is received from an object decreases as the distance from it squared. So this is all of the equations and relationships that are needed for the event on this slide and on the last slide. So the radiation laws and the fundamental equations and relationships. So this is all that will be contained, all that will be necessary for the nationals level astrophysics calculations. Okay, so now I want to run you through the resources that we have available for the event this year. So of course, the NSO store has great resources for fundamental information. And each year, some of the early invitational tests and answer keys are posted on the NSO website. And we also post webinars on the Chandra and Universe of Learning website. And there will also be a corresponding link to them on the NSO website. Accordingly, the PowerPoint PDFs of this presentation will also be posted on the NSO website, and the webinars will be posted on the Chandra website along with the transcript. So you'll be able to find the information both on the NSO website and on our Chandra website, which I'll show you in a second. And NASA's APOD website is another great place to find further information about deep sky objects. This has an astronomy picture every day. It's a great, just put it on your browser tab and refresh it every day, and you'll have a new interesting image to think about with a little blurb explaining what's going on in that image. Then there's also excellent websites for basically every NASA observatory. So I recommend finding images and finding information by looking for a given object. So say RS Puppis, and then search RS Puppis plus NASA. And then you'll find a range of NASA websites that go into detail on the specific deep sky object. And I really strongly recommend focusing on the NASA resources, because there are excellent NASA resources for the vast majority of the material in this event. So here's the Chandra website that I was just mentioning. This is our primary Science Olympiad informational resources webpage. So we include content webinars every year, transcripts and presentations from Science Olympiad alumni and NASA astrophysicists, our science mission experts. These are posted on the Chandra website, and we'll be kind of continuing to add material here over the next few months until the end of the fall, at which our competition season begins. And so I strongly recommend accessing this website to get kind of fundamental information for the event and to view the webinars after SOSI ends up. And then you can also use Chandra to access the JS9 guide that we've put together. This is a great guide to learn the fundamentals of JS9 and to play around with the actual way that astronomers analyze images and study our universe. So I strongly recommend using this tool and having your students really get into the details of image analysis. And especially if your students are going to nationals, we always include JS9 questions at the nationals level. One other thing to mention is this event is sponsored by the Universe of Learning, and the NASA Astrophysics Division has organized a Universe of Learning STEM informal education outreach program. The NSO is one of the Universe of Learning partners, and Science Olympiad alumni are developing resources to support the program and partnership. So the Universe of Learning website, as you see here, has posted several of these resources already, as well as resources created by other organizations and missions. And they also have information that is helpful for Science Olympiad team preparation for competition. And so one great section that will be most helpful for your students is the how do we know all of this and the how do stars form, live, and die sections. There's also the Universe Unplugged section, which has several webinars that are posted that cover a multitude of topics. And additionally, some of the NSO resources are listed in this section, and soon every single resource from our webinars, sample tests, JS9, PowerPoints, and transcripts will all be available here. So we're slowly migrating our material from the Chandra website to this Universe Unplugged website through the NASA Universe of Learning STEM Informal Education Outreach Program. Okay, so I just want to finish off the way that I like to finish off every webinar type presentation by just giving you a list of the resources that are available for the event across the electromagnetic spectrum. Of course, there's the soinc.org website and the universeoflearning.org website, but then there's a wide variety of other websites through NASA that are excellent ways to understand the detailed properties of our astronomical objects, our DSOs, across the electromagnetic spectrum. And lastly, I just want to give a brief rundown of event information. There's my email. I'm Tad Komacek. You can email me if you have any questions about the event. And I'm a co-supervisor with Donna Young, who's really the brains behind all of this. Donna has been doing this for a long time and has developed an amazing event. And so you can feel free to contact either of us if you have any questions about the event. And I just want to give you a quick rundown of how to prepare for the event. So I recommend, of course, starting out by, after this, reading the event description for the content in detail, and in the fall, using the webinar for an overview of the content topics and deep sky objects, and using, of course, the coach's manual, which we've built up now for a very long time, over a decade, as a guide for background information. And then I recommend using the resources that are listed in the event description and in the presenter notes of these slides for further images, further content, and further links. There's also great videos, of course, on YouTube, and using tests, practice tests from invitationals and sample state tests that we'll be posting on the NSO website over the course of the year. So anybody can use these tests for practice, and those will be developed by us, by the NSO A team, we call ourselves, which is our collection of alumni and other educators that have been developing astronomy resources throughout the last, at this point, over a decade. And we also, of course, strongly recommend using the sciole.org test exchange to exchange tests between students, so from peer-to-peer rather than from top-down. And then for the advanced students, I strongly recommend that they look at college courses, for example, Astro 101 introductory college courses, the materials for which you can find online. And additionally, looking at scientific papers that correspond to the individual deep sky object of interest. And so I'll just finish by leaving my email contact information up. And I just want to say thank you so much for viewing the online SOSI presentation. And we look forward to seeing you in person at SOSI next month. Thank you so much.